All right, so I've already given you two examples where growth factors, specifically IGF-1, wasn't required for the increase in muscle mass from resistance exercise. One was the Spangenberg paper where they showed that the MKRs who had a knock-in receptor for IGF-1 IGF-1 couldn't activate protein synthesis or any signaling in the muscle. They still hypertrophied as a result of resistance exercise. And I also showed you the work from Hamilton and colleagues where after resistance exercise, the P85 associated with IRS1 actually decreased, probably because of that feedback from S6 kinase to block the ability of IRS1 to signal. And some of the first work that showed that you didn't need this AKT-mTOR signaling pathway to cause muscle hypertrophy was done by Troy Hornberger. And this was an in vitro stretch experiment where he took a muscle, it was a small muscle, and he started using a little dynamometer, which basically just twitched and stretched the muscle. And he would do that for up to 90 minutes. And what you can see is the amount of protein synthesis per milligram of protein per hour would go up. So protein synthesis specifically at this 60 to 90 minutes, where they've stretched the muscle for almost for 90 minutes basically, what you can see is that there's a big increase in the amount of protein that these muscles are making. Okay, so then what he's got is he's got this isolated muscle in a dish, and he can start throwing things into it to see what was required to increase protein synthesis. So just to go back through it, he used insulin as a control, and that's on the left side here. And insulin as a control to say that let's look to see how signaling goes. So here's phospho-AKT or PKB. Here's P70S6 kinase as a measure of mTOR activity. And then what they did is they gave either a vehicle, so just like ethanol, which is what these things are, the drugs are dissolved in, rapamycin, which I've told you blocks mTOR, or wortmannin, which blocks the PI3 kinase. So if you give insulin with no inhibitor, you see AKT gets phosphorylated, and this results in an increase in mTOR activity. If you give rapamycin, which blocks mTOR, you still see that AKT gets phosphorylated. It actually gets phosphorylated a little bit more than it did in the vehicle treatment group. But S6 kinase now doesn't get phosphorylated because you've blocked mTOR. Now, if you give this PI3 kinase activity or inhibitor, and remember, we get AKT phosphorylation, which is downstream of PI3 kinase going up to the membrane, making PIP3. If you block PI3 kinase, you don't get activation of AKT, and you don't get activation of mTOR. So now what he can do is go back and do the exact same experiment using stretch instead of insulin. So when he stretches in the presence of the vehicle, the first thing that's interesting is that there's no activation of AKT. But there is activation of S6 kinase or mTOR. And you can see that the activation of mTOR is actually higher than it was with insulin. All right, second thing, you do the stretch, but now you add rapamycin, completely block mTOR activity, just like before, no difference in AKT phosphorylation. If you add wortmannin, now again you've completely blocked AKT or PKB phosphorylation, you still get exactly the same increase in S6 kinase or mTOR activity as you did in the presence of, or in the absence of wortmannin. So even when you block AKT completely using this drug that blocks PI3 kinase activity, normally if it were insulin, that would block mTOR activation. But with resistance exercise, it doesn't block mTOR activation. This tells us that insulin and resistance exercise are working differently in how they activate mTOR. So then the paper that I gave you for this section is the Jacobs paper. And Jacobs is the first author, did most of the work, but the last author again is Troy Hornberger. So he did the last study on the stretch, and then he opened up his new laboratory and he started doing other experiments to try and figure out, so if it's not AKT mTOR after resistance exercise, how does it work? Okay, so the important data here is that he did eccentric or resistance exercise, and he measured TSC2 by Western blot. And Western blot, again, you denature the protein, you migrate them down, and if the protein is heavier, that means that it's had little additions been made to it. So you can get some phosphate groups put on if it's phosphorylated. You can get acetylated. Anything can make it heavier. and the charge is going to change as well. So now what you're doing is you're using a negative charge to push, but now it's a bigger protein. So now what they saw after resistance exercise was you went from this thin band to a thicker band. And they thought, well, maybe that's because it's phosphorylated. So they treated with a phosphatase. And what they saw is that the band migrated faster, both at rest and following resistance exercise. And what that suggested to them was that TSC2 was phosphorylated after resistance exercise. And sure enough, they used a specific antibody to this sequence of RXRXX and then a serine threonine that's been phosphorylated. So this is an arginine, any amino acid, arginine, any amino acid, any amino acid, and then a serine threonine. So this is an antibody that recognizes a small protein, a small bit of a protein, a small peptide, where the serine threonine is coming after a couple of arginines. And that's a signal for some specific kinases. Okay, and what they found is after resistance exercise, when they used this RXRXX-ST antibody, they saw a significant increase with resistance exercise in the phosphorylation of TSC2 at this specific site. Suggested that a kinase can phosphorylate this, but they didn't think it was the kinase PKB because, again, they had done the earlier work. So now what they did is they did this really cool study. And what they did here is they used a bunch of different markers. Here's a muscle fiber here. You can see the outline in blue, that's laminin, and that's the muscle membrane. LAMP2 is a protein that's found in the lysosome, and then TSC2 is that protein inhibitor that's becoming phosphorylated. So in the control situation, you can see dots that are green, here, 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 and here, and dots that are red, TSC2, and they co-localize. And you can see that kind of in this area here where you can see big dots of red and big dots of green, and you get this yellow compound. After resistance exercise, what you can see is you see these green dots, but you no longer see the red dot connected with the green dot. Okay, they then quantified it using this really cool technique here, but it's the easiest to see in panel M here, where you look at the intensity of the co-localized pixels. So now they're looking for red together with green. And red is always together with green in the control, and after the resistance exercise, the red is no longer together with the green. So what this suggests is that in mouse muscle, that the TSC2 has moved away from the LAMP2, and LAMP2 marks the lysosome, and that's where we think that mTOR is. So basically what's happened is that TSC2 has moved away from mTOR, and it's specifically mTOR's activator, REB, and TSC2 is an inhibitor of REB. And so that resistance exercise has resulted in the activation of an RXRXX serine threonine kinase. When that kinase is activated, that kinase can phosphorylate TSC2. When TSC2 is phosphorylated, it moves away from REB, and that's the signal now to activate mTOR. That somehow we've cut out the top part, the PKB requirement, because there's a different kinase that's coming in to phosphorylate TSC2 at this specific site. Okay, so what if you do it by cartoon measure? There's this unknown sensor within muscle that's changing the load sense. It's sensing load, and now this kinase becomes active. And when it's active, this kinase can come in and phosphorylate directly without going through this long cascade of events. And this kinase can become active for much longer than PKB can become active in response to IGF-1. So now we've got this kinase that's on for a long time, phosphorylating TSC2 and moving TSC2 away from REB for a long time. And now we've got this prolonged activation of mTOR, which is going to give us muscle protein synthesis and muscle hypertrophy.